Hello, my geeslings. This is Mother Goose Robinson Earhart introducing this week's episode, or this Monday's episode, of Robinson's podcast, number 19. My guest is Nick Huggett, who's a philosopher of physics and science at the University of Illinois at Chicago. Before that, he studied philosophy and physics at Oxford and then Rutgers. We get into how Nick became interested in physics and philosophy, and then from there we go straight into the meat of the episode, which is Zeno of Elea and his paradoxes of composition and motion. And those paradoxes are actually some of the first puzzles that got me interested in philosophy, particularly the paradoxes of motion. Because even if you're not a trained philosopher or a trained physicist, they really grab your attention as being problematic. I think Nick did a particularly phenomenal job in this episode accommodating me because I know vanishingly little physics. And so he had to contend with my very naive questions, as I'll put it. So I really appreciate him giving me his time and also explaining things with the simplicity that I needed to hear. So, for instance, we talked a bit about string theory and quantum gravity, which, as you can imagine, not being a physicist, are very foreign from just daily intuitions and also require a lot of technical expertise. And I asked a lot of questions that I think were difficult to grapple with just because they didn't make sense to him within the conceptual framework of physics. But like I said, I really appreciate that he didn't just stop talking to me or something because I was frustrating. So I really enjoyed this episode. I got a lot out of it, and I hope you enjoy it as well. There are definitely more philosophy of physics episodes to come because it's just something that has really been grabbing my attention lately, even though it's not something that I'm studying. And I guess I do wonder how much I can learn without devoting time to the study of physics itself. But I'm still hoping that I can get a general understanding of the lay of the land. And as these episodes come out, as I conduct the interviews, hopefully through me, you'll also be able to get some sort of understanding of what it is that a philosopher of physics is researching. So I hope that you enjoy the episode and let me know what you think. How did you get into physics in the first place?
Yeah, I think it was just a subject. I just always enjoyed the science subjects. And in the UK, you sort of specialize much earlier than in the US. So in the last 2 years of high school, where you take the A levels, the final exams, from high school you pick 3 or 4 subjects. That is the norm. And they tend to sort of track you either into sciences or humanities. So the things I was best at and enjoyed doing was, physics and mathematics, and then I added chemistry, which I didn't enjoy as much and wasn't as good at. So that's how I ended up doing that. So it was always something I enjoyed a lot. And that's kind of how I developed the sort of physics speciality.
Did philosophy come later, or that was always part of it?
Yeah. So, as in the States, there's the main courses you're taking, but you'd also take various electives. And I guess I did find I was taking electives that were more on the philosophical side. And I also sort of found I was just getting a little frustrated with only doing science subjects. So when I when I was thinking about going to university, also you specialize, at university level. Everyone applies to read a particular subject at university. It's not something you kind of figure out when you get there, which is much more common or the norm for people in the US. So, I kind of, knew I should be doing physics because that was really what I wanted to do and enjoyed doing, but I also felt that wasn't enough. So I was pretty happy when I discovered that you could do philosophy of physics. So so that was how I ended up doing that. So
is that what you studied at Oxford, philosophy of physics?
Yeah, so they have a joint degree.
Okay, so I think they're very strong in that area, right?
Yeah,
their department.
So
that must have been a nice place to be.
Yeah, I mean it was pretty different. Now they have sort of half a dozen faculty teaching philosophy of physics.
Oh wow.
There was really just one person at the time who they just hired who was teaching it. And in that degree program in the whole university, there were only 3 of us in my year that were doing that out of whatever, several thousand, a few thousand people. It's much, much bigger now. Many more people take it.
Mm-hmm.
I think, a lot of the people who work in philosophy of physics, I mean, I think this was also part of my motivation for we're not just studying, but then sort of sticking with the subject. And what I really liked about the subject was, there's a certain kind of person who takes physics classes and starts to kind of ask more why questions than most physicists. Why, you're taught the material, and I think people who become good physicists often, they pick up the lessons and learn how to do the physics really quickly. But there's another kind of person who's, I think, good at the physics, but also wants to know a bit more about why we do this thing rather than that thing, and starts to ask the kind of questions that lead to philosophy of physics and are the kinds of questions ultimately philosophers of physics ask. And I guess I found I was one of those people.
Mm-hmm. Yeah, Columbia has David Albert, who I unfortunately never got to take a course with because I was always working on more logic-y things.
Right.
But and then at Stanford has Thomas Reichman, who hopefully I'll be able to do some studying with as well. But I, in high school, sort of went the opposite route, which I rue now, in that I started getting interested in philosophy and only later have gravitated towards more technical areas in the field. I wish I had that science background from back then. But when I was in high school, one of the first philosophers whose work spoke to me, though I didn't know much about it, one of my teachers told me about it, was Zeno of Elea, who I was hoping to talk to you about today, because his paradoxes, they're very easy to grasp even for somebody who isn't philosophically trained. So first off, why is somebody who was doing physics or primitive physics like 2,500, 2,000 years ago relevant to us now?
Yeah. So I don't know that I would say, it depends who the we are, whether he has things to tell us about, to tell physicists today, I think is more questionable. I mean, I regularly get emails from people who think he does, but I think many of the sort of main problems that he raises were solved in the latter part of the 19th century. So with the proper foundations given to analysis, the theory of real numbers, and the foundations of the calculus, I would say solve a lot of the problems that he raises.
Because, I mean, jumping a bit ahead, they have to do with the continuum,
right?
Roughly, okay.
Yeah, understanding the infinitesimal, and
Yeah, I was excited to see, because I'm working on infinitesimals right now, that one of his antinomies, that of there being large and small, revolves around infinitesimals on some level. But so, what is the earliest physics that we really know of?
Yeah. Well, it depends what you mean by physics, which I guess is a question you asked me
In
earlier,
our first episode,
perhaps. Yeah. And maybe the answer I give will be compatible with what I said then. So it really depends. So, as I think I probably did say then, if you really think about, physics in the modern sense as, application of, rigorous, careful, empirical methods and application of, mathematics in a careful way, then really that the sort of systematically starts in the 17th century, in particular with Newton and various other physicists, people at that time. So in the modern sense, but kind of working backwards. People started, in the medieval period. People started to figure out there were mathematical developments then that people used to start to do something along those lines. I should say my knowledge here is, largely in the sort of Western tradition. So I know, in the Arabic world, in India, there was also work done that people you might count as physics that I know a lot less about. Working backwards to, then to antiquity. So you think about, of course, the key question people were interested in then that sort of looks like physics and is really the sort of origin of physics is the problem of the planets. Right? Mm-hmm. So, people, if you look at the sky at night, it's what you see. If you look, over the night, you see this fixed canopy of stars that's apparently rotating around the Earth. And of course, during the day, you can follow the moon and the sun, also rotating around the Earth, apparently, once, every 24 hours. You also notice that day to day, they change, with the years, exactly what the stars, which stars, rise first, exactly which ones are overhead. That changes over year as the Earth, as we now know, moves around the sun. And moreover, that, of course, is fairly straightforward to predict.
Very quickly, though, the problem of the planets then is sort of coming to grips.
But that's the bit I'm coming to.
Oh, okay. Well, then, go ahead.
Right. So that's fairly straightforward. You sort of have a 24-hour period, and then on top of that, you have a 365 and a quarter day period. And, but when you see that and you can draw a map of where the stars are, that's regular in a way that's not so hard to kind of predict how things are going to be from year to year and predict the seasons. And of course, this had important implications for agriculture, important implications for religion. So there's a kind of that's empirical, that's mathematical in a sense. And so, but what you also notice, of course, is that some of those stars actually don't stay in a fixed position in the sky from day to day, or relative to all the other stars. They in fact move relative to the stars, whilst moving daily and moving annually. But it's like you have a star that sort of from day to day is in a slightly different position relative to everything else. And those people Greeks called the wanderers, or the planets, as we talk
the
now.
Wanderers. That's a nice name.
So that's and the sun and the moon, of course, are wander in that sense as well. If you now think about them, and there's also objects sort of in the sky, they don't stay in a fixed place relative to the fixed stars either. So they're, in the Greek sense of the word, they are also planets, and the Earth isn't, because that's at the center of the universe. So that's the problem of the planets, is to give the laws that describe how the wanderers actually wander through the sky over time. And that's sort of the birth of physics, because it is something that's sort of mathematical, that you need to, the way you're going to describe it. So you can make you can make predictions, but it also happens very slowly, and people were watching the skies, for hundreds, thousands of years, and so collected what amounted to very sort of accurate data about how the planets move. If you make a prediction, people are going to be applying that prediction for the next 100, 200 years. And if your prediction is wrong, that will eventually become apparent and people will try to make a better prediction. So that's sort of the origin. The Babylonians, well before the, before the Greeks, back into antiquity, people had tried to have theories of this in the Greek period. So I think Eudoxus is one of the people who tried to sort of solve this problem. Has a story about, and then Aristotle has a story about how this happens. And I mean, of course, that's indeed the problem that Newton wanted to solve and did solve with universal gravitation. So that's the sort of origin of, I would say, of physics. Aristotle has a book called The Physics, which sort of deals not quantitatively but sort of qualitatively with how that story is supposed to work, but also interested in other kind of issues. For instance, what the elements are, what gravity is, what's the difference between light things and heavy things, issues like that.
Did the Greeks realize that what they called the wanderers were planets, or did they think that they were just stars? Because I can imagine without all of the technology we had looking up, seeing some that were fixed, some that were moving, that would raise serious existential questions about their place in all of this.
So, so the kind of standard picture was a picture of sort of nested spheres. So on the fixed stars, you would think were thought of as being points of light, sort of fixed to an outer sphere that's kind of rotating. The Earth in the middle, that's rotating around once a day, once a year. Okay, and then it has the sort of annual motion as well. That's like to explain the difference from day to day rather than during each day. And then within that, there would be a series of other nested spheres, each one with one of the wanderers attached to that sphere, something like that.
But they were just points of light to them. They weren't necessarily planets.
So that's a good question. So there's nothing sort of fundamentally different between the stars and the wanderers in that picture. They're just on different stars. So there is Of course, the question comes up of why, what causes them to produce this light. It's pretty clear that the moon, for instance, is reflecting the sun's light because we have eclipses, and you can see it's the Earth's shadow being cast on the sun, on the moon. Incidentally, that also makes clear and was well known to the Greeks that the Earth is round because of the shadow that it is always a part of a circle you see cast. You never sort of see the sun casting a shadow as if it was on edge or anything, it's really clear. Anyway. So I think so if I remember this right, I think it was kind of a puzzle about exactly why the planets, why the stars glow. I think Aristotle had one suggestion that it might be friction as they move against each other. And of course, this was a question that was not answered until the discovery of quantum mechanics and nuclear fusion. Mm-hmm. So sometime in the early to mid part of the 20th century that we came to actually understand how stars could be producing the amount of light they were. But at least the Aristotelian picture of the universe, everything. So we have the Earth that's made of earth, the element earth, and there's water there as well. The other two terrestrial elements are the air and fire. So obviously the air is sort of the atmosphere, and he needed fire to understand how things could be light, and because you see flames sort of shooting up into the air. But everything outside the terrestrial realm, so basically once you get to the moon and beyond, is made of a special element for the heavens, the ether.
So back to Zeno now, who, if I'm not really mistaken, is best sort of known today through Aristotle and Plato, and then because of his relation to Parmenides. But where does he sort of fit into this early picture of physics and with his paradoxes?
So I think one of the things I like about Aristotle's sort of understanding of physics, sort of conceptually, was his understanding that motion and change is the key. So he's very interested in change in general, and locomotion, motion through, of objects in space in particular. So, and Zeno in many ways kind of challenges that. I mean, Zeno also challenges our sort of understanding of how, of composition, how finite objects could in some sense be composed of infinitely small objects. I see this, these questions as challenges for the mathematics one kind of assumes or would use to sort of talk about these things. And I think Zeno sort of successfully points out that, I mean, it's a kind of anachronistic way of putting it, but effectively what he successfully points out is limitations in the kind of mathematical tools that they had to actually talk about these things.
And that I would gather is primarily with regard to his paradoxes of motion rather than those of size, or maybe I'm
well,
mistaken.
I meant that I was bringing in composition as well to
Okay.
mean that, yeah, also.
So something that I found interesting as I was looking into this was the etymology of paradox. So paradox comes from the Greek para, which is against, and doxa, which is belief. So it's really just taking, I guess, premises that we might agree with and then coming up with a conclusion that is contradictory to our intuitions or how we view the world. And as I was reading about his paradoxes, that seemed to be exactly what was happening. I mean, I found myself agreeing with the premises as he laid them out as put by Plato or Aristotle, and then finding that the conclusions were utterly sort of foreign to my experience of the world. So I'd love to talk more about these paradoxes in particular. Are there ones that you would want to start with, the motion or composition?
Yeah, we can talk about a couple of them. That sounds good. Yeah, no, that's a nice point. I like the etymology, the point of etymology about paradox. Mm-hmm. I mean, I'll say in our sort of modern, that's kind of a nice way of putting it. I think in sort of contemporary use, people mean a lot of different things by
I think
paradox.
It's just contradiction.
Yeah, that's one use, but I think people will use the term even to just mean sort of surprising or kind of unbelievable conclusion, rather than literal contradiction and a range of sort of things that can happen, sort of in between. So, yeah, from sort of unbelievable to clearly false or something to contradiction. So, yeah, I think it's worth kind of bearing that in mind.
That we're taking our beliefs and then
that's a nice general way of putting it.
Against them.
Yeah, yeah.
So which of the paradoxes would you like to start with?
So,
There's one that I don't really understand. Maybe we could start
Sure.
with that one.
Sure.
So the paradox that there are not many things. So it seems like a sort of very... Well, was Parmenides a monist? I think that would be the technical term for it. Somebody who only believes that there's one thing.
I think that's right. Yeah.
Yeah, and I mean, that seems completely contradictory to our intuitions about the world. I mean, here you are, here I am, here my cat is. There have to be more than one things. But I actually heard recently on a podcast that might have been with Sean Carroll. You're familiar with Sean Carroll, right? His Mindscape podcast. I'm not recalling the professor's name, but he's at Rutgers, and he is a monist today. So it's not at all dead belief. He just thinks that there is the universe and there is nothing else. But it's kind of, it seems to me to be sort of twisting the words
Right.
But anyway, so the first paradox that is in the SEP article is called, I think, the antinomy of the many. But it's the idea that there is only one thing, because if we suppose that there are many things, it leads to contradiction. So what is the paradox of the many, and why would it lead us to suppose that there's only one thing, which just seems to run entirely contrary to the way that we view the world?
Yeah, right. So I think there's a number of considerations that appear here. So I think if I remember right, the best form, the general form of the argument is if there aren't, assuming there's something, I think we're putting aside the idea that there's possibility that there's nothing. So if there's either one thing or some finite number of things greater than one or some infinite number of things. Okay, those are sort of the options that are on the table. And if I remember the argument correctly, first of all, we say, well, suppose there are finitely many greater than one number of things. Zeno seems to have the idea we're imagining them in space so that we could actually distinguish the things. So he's sort of imagining maybe something like an object, and is it composed of more than one thing? Well, if there are two parts, he thinks there has to be something in between them to distinguish them. So there couldn't just be two; there'd have to be three. But then to distinguish the object into three parts, there'd have to be a part between the first and the third, and between the first and the second and the third. Mm-hmm. And so there are five things, but there couldn't be five without
infinite.
Right. So we keep going, and there'd have to be infinitely many things. So I'm not saying that's a great argument. It involves some strange assumptions, I would say, but that's the argument that he gives against there being finitely many things. That's okay. So maybe this object is made of infinitely many things. But now you have to think about, I think Zeno, here it's less clear what Zeno has in mind, but looking at some of the other arguments, the kind of thing he would then worry about is, well, look, okay, so I've got my object, this table, I've got an object. How many parts is it made of? I guess the object is the universe, really, if we're thinking about this kind of monism. How many parts is it made of? And so just think about an object laid out in a line. If they are zero in length, Zeno thinks, then, well, add up as many zeros as you like. You still have zero, so it's going to be nothing. I'm going to be back to nothing, so that can't be the way it is. The alternative to them being zero in length is that they have some sort of finite length, but an infinity of finite quantities, he thinks, is infinitely big. But so that the only way to have infinitely many things is to have an infinite universe, or every objects to be infinite. And I think he wants to reject that. So, by the lights of, I think there's a number of kind of questionable assumptions, questionable from the point of view of sort of physical composition, but sort of particularly questionable from the assumption of mathematics as well.
Right.
Although, as I said before, these things weren't properly understood, they were sort of intuitively understood, but they weren't kind of put on a rigorous footing until the 19th century. where people really understood how to say these things in a way that they really knew was on solid mathematical grounds and not just sort of intuitive ideas about how numbers are, but actual work by sort of people like Cauchy and Weierstrass that developed the calculus that we have now. So we actually have a formal, well-defined theory of how to handle infinitesimals, which banishes infinitesimals, but loosely speaking. So, for instance, one of the assumptions was, and this will may come up in some of the paradoxes of motion. Well, whenever you add up an infinity of finite numbers, the answer is infinity, and that's just wrong according to the calculus.
Right.
So there's that. I think the other assumption was, and this is a a little more sticky one, that an infinity of zeros is always zero. So adding up is not really. So that's developed then in the in the theory of real numbers in analysis, right? So you sort of think about a segment of the real numbers, say from 0 to 1. In the theory of analysis, there are an infinity of points in that line, and an infinity of numbers between those two, including those. So, each one of which is, according to sort of theory of length that we apply to the real numbers.
Measure theory.
Exactly, measure theory. In the standard measure, each one of those indeed has length 0. But, there's two things to know. First of all, there's more points in the line than there are numbers in the sequence 1, 2, 3, 4. Right?
It's uncountably infinite.
It's uncountably infinite, so there's more than there are natural numbers. So it seems addition doesn't even make sense, because addition always involves adding two numbers, and then a third, and then a fourth, and then a fifth. So addition is a notion that's only defined when we have countably many numbers.
Right.
So, of course, instead we have the integral and the standard measure on the real numbers, and that gives us an account of how all the points have, according to within that theory, all the points have 0 length, but that part of the line has length 1. So that, there's sort of important. I think the important sort of philosophical and kind of conceptual issues here then are, insofar as Zeno is challenging the sort of mathematical representation of matter of the universe. We do now have met that challenge insofar as there is a mathematical theory of how we can have the infinite divisibility and 0 length parts, and of adding up to constituting, in that sense, a finite length. Of course, the remaining question is the applicability of that mathematics to the world. Is that actually the right structure for thinking about the world? So, we probably won't actually get to talk about quantum gravity. One of the things that seems quite possible in that theory is that there is a smallest distance. So,
the
Planck length,
maybe
10
we
to
will...
the 32 minus 32 meters, and so actually we shouldn't be, at the fundamental level the calculus doesn't apply, and we have finite numbers of things sort of adding up, but we take them to be distinguished. We're rejecting other premises. We deny that we deny that to be distinct there has to be a third thing between any two things. There's that questionable premise, and there's also the premise that the universe is finite is questionable. So
in the quantum gravity world, then calculus just
even Newton rejected that, right?
Becomes a powerful heuristic, though.
Yeah.
So maybe we will get briefly to this quantum gravity when we talk about the stadium, which is the next paradox of Zeno. That I think that's the one that I initially... the tortoise and the hare, or the Achilles paradox, is the one that is most popular, but I think the stadium is the one that has always gripped my imagination the most, just because it's I mean the simplest of them all, and it's the one I think I heard first in high school.
Yeah, no, I agree with that. The Achilles, the tortoise and the Achilles is, I would say mathematically, yeah, it's kind of gripping. It's kind of a very kind of gripping story, but the mathematical point, I think, is basically the same.
So, do you want to explain the stadium, or should I, or you can, or?
Yeah, no, I'm happy to.
Okay.
So it's also called the dichotomy paradox because it involves dividing into two.
Okay, that's a good name.
So that it's also called that. It's based on division into two. And Zeno asks, right, how can imagine a runner at the beginning of a 100-meter race. Zeno would ask, well, how can the runner actually get to the end of the course? Because think about their run. First of all, they have to run 50 meters to get halfway. And after that, they have to run 25 meters to get half the remaining way. And after that, they have to run 12.5 meters to get half the remaining way. And after that, 6.25 meters, and so on and forever. And so endlessly, there's an infinite number of half distances that the runner's going to have to cover before they get to the end. And how could they ever complete an infinity of finite distances? It's clearly sort of impossible. And there's different grounds in which that might be. You might think of that as impossible. One is there's no last one they have to do. So if there's no last one, how could that happen? So Aristotle, I think, has a decent answer to that part of the problem. Namely, well, look, suppose it's a fast runner and they take, say, 10 seconds, to finish the race. Well, it's fine. They got 5 seconds to do the first half. They got 2.5 seconds to do the second part. They got a second and a quarter to do the next part. They've got, whatever it is, to do the next part. The 10 seconds it takes to do the course can also be divided in the same way, and so there is a piece of time ready to do each one, and there's no end to those times, but they make 10 seconds, and so it's all kind of fine. Perhaps but another aspect of the problem that I think Aristotle sort of neglects or glosses, sort of takes as being too easy, is, but look, it's still, there's a finite. I've now divided the time up into this infinity of finite pieces. But surely, if I add up, if I have an infinite number of finite numbers to add up, my sum keeps getting bigger every time I add another one. So won't that equal infinity?
Right.
So in fact, that 10 seconds. Back to
that other paradox.
Yeah, similar kind of. Yeah. So won't that, in fact, that 10 seconds really turn out to be infinitely long? And so I have another form of the paradox. Aristotle's, you're just assuming there's 10 seconds, but once you say, well, I can break my 10 seconds up into all these pieces, and there's one for each one. Well, now it turns out that what you thought was 10 seconds is instead, or also, an infinite amount of time. And clearly that's now contradiction, or just means the runner can't move. So yeah. So, I think people had the intuition, sort of even then, and certainly, by the 17th century, people are reasoning this way. But look, I keep, when I sort of add a half to a quarter to an eighth, to a 16th to a 32nd, which is effectively what's being done here. It gets ever close. It just keeps getting closer and closer to 1, but never quite reaches there. That doesn't add up. It just doesn't add up to infinity. If it sort of I'm going to, I'm going to treat it as, in some sense, that sum is equal to 1, right? But just as, before when we were talking about, how can an infinity of zeros add up to a finite number, we sort of have a puzzle here as well. Addition really, as I said, requires adding 2 numbers together and then another one. So any actual sum is not only countable, it's actually finite. Addition is an operation on numbers that tells you what to do when you have 2, and if you know how to add up 2, then you know how to add up 3, and you know how to add up 4, and you know how to add up 5. There's no longest sum that you've defined now how to add up, but that doesn't mean you've defined what it is to add up an infinity of numbers.
Right. I remember for Aristotle, to be a number just means to be countable. So infinity, in a way, isn't even a number in his worldview.
Yeah, that's probably right. So yeah.
Mm-hmm.
Yeah. So basically, like I'm saying, so you start with addition, and that sort of now covers when you have finite collections of numbers you want to add up. The next stage you can go to is the one from the stadium, where you now have, a countable infinity of numbers you want to add up. There is a first one and a second one and a third one, but there's no end to that sequence. And then beyond that, there's when you have uncountably many numbers. That's when we, talk about integration and measure theory. For the countable infinity, what we need is a definition of what it is to add those things up. And of course, it is the intuitive idea that kind of comes from Cauchy and people learn in their calc or pre-calc classes, that we define the sum of an infinite number of terms to be equal to the limit of the partial sums. Add up the first 2, then add up the next 3, add up the next 4. We now get a sequence of numbers. The limit, if it exists.
I think that's Calc 2, not pre-calc.
Really?
Yeah. Well, I think Calc 1's more derivatives, and then Calc 2 is more integral calculus. Yeah. Pre-calc is just like algebra.
But you don't do like an infinite sum?
Maybe we do. It's been a while. I think maybe it was infinite series and things like that was Calc 2.
Okay. That seems easier than calculus, than infinitesimal calculus. Okay, but yeah.
And so this is where I guess we would get into quantum gravity from a distance. But the reason being, when I first heard this paradox, my intuition was, I guess, there just can't be an infinite number of subdivisions in space, the way that this paradox would have us believe, that you can always have all of these distances, because to me it just didn't seem feasible that you could complete an infinite number of tasks in a finite amount of time. So if you have 10 minutes to run this race, and there are an infinite amount of sub-intervals in this 100-meter interval, then you just couldn't do it if there were an infinite amount of them, no matter what the math tells you is possible, because the math is just an abstraction from something else. And then at some point along the line, I read this book by Brian Greene, who's do you know the name? I think he's a physicist at Columbia, but he writes a lot of popular books. And in this book, there was maybe a chapter or something on string theory. And of course, you'll correct me when I'm wrong here, but maybe some aspect of string theory. I know last time we talked, you told me there are multiple camps in string theory and in quantum gravity, but at least in one of them or somewhere, there's sort of a smallest unit of measure, maybe like the Planck length or something like that in space. And is that a possible solution to the paradox? Like you just can't stop breaking down space infinitely?
Yeah. I'm hesitating because I think the...
Well, if you could rephrase that, I mean, I didn't do a good job of it.
No, that's okay. Sure, let me... I got the question. So yeah, that would be I'll give you a point where you can kind of cut from, I guess. So yeah, that would be another way to solve the problem. I guess I am hesitating a little because I'm less reluctant than you to accept the solution that was provided by the calculus.
Oh, so you're less hesitant to accept that.
I'm not hesitant at all. That is the solution to the problem. Okay. Sorry, I don't... Yeah,
that's the solution to the sort of real world problem, or just the thought experiment problem, or both?
So, if quantum gravity turns out to be right, then you're right. Then there's a different way of sort of understanding, or we would understand things differently. But if space and time turned out to be continuous, as Newton thought and kind of people thought well into the 20th century, then I don't think Zeno is raising any sort of serious problems. Then the calculus is telling us how to resolve those difficulties, and that is the correct way to represent the world and to think about how things are happening. But you're quite right. So I don't see Zeno as sort of motivating in that way. It's not like there's some unresolved problem that we need in Zeno that we need quantum gravity to resolve. But you're right. Things would look different. There would be space and time would be in some sense constituted according to a number of approaches to quantum gravity of smallest elements of the Planck length, and so any region of space or any object would ultimately in some sense be composed of however many Planck length sized objects. So people come at that conclusion in different ways in different approaches to quantum gravity. I think maybe you were thinking of loop quantum gravity in particular has a prediction of a minimum area, the Planck area, which is the Planck length squared as a sort of smallest region.
Why would it be two-dimensional?
But that's just how the mathematics kind of works.
Okay.
So
in my mind, it would be like there would be some, I don't know, I guess it would depend on how many dimensions of space, or if it's not space, time, whatever other dimensions there are to the universe, there would just be some like pixel-like entity that would be like the small, I don't know if it would be an entity, but a space for an entity to fill that would just be this smallest unit squared cube.
So if space is three-dimensional, then it would be the Planck
cube.
Volume.
Yeah, Planck volume.
Yeah. So I mean, a lot of the arguments, it comes out to be the Planck volume.
And what in loop quantum gravity do these sort of small, I guess it's areas, the Planck areas, I don't even know if it makes sense to ask what it looks like, because what something looks like is probably dependent on the light reflecting off of it. So looks like isn't the right way of asking my question, but what is it like, I guess, might be the question. Does something fill it? Is it like a pixel on a computer screen that just lights up when something passes through it? Or I'm thinking right now, I guess I took a class on David Lewis a long time ago, and you probably know more about this than I do, but one thing that I recall very vaguely is this idea of the Humean supermosaic, where the universe is just a bunch of different points with qualities, and what we see supervenes on the Humean supermosaic. But I guess I'm wondering what these tiny Planck areas are like, if that question is something you can work with.
Yeah. So I don't think it's at all like the way you're picturing it here, right? You're sort of trying to picture this as, little chunk of space, and within that space, everything is the same or something. It's all red or something like
Yeah.
that, like a mosaic. No. The idea has to be that it makes no sense, sort of at all. It makes no sense to ask what it's like inside that region or what that region itself is like. If you go beyond that, in some sense, you're probing beyond where there is any space and time.
Mm-hmm.
Space is just sort of is granular, and you're sort of trying to think of those smallest regions, and how else can you think, sort of against a background of an actually continuous space. But those things make up the space, so there isn't anything kind of smaller than that.
Mm-hmm.
So you sort of had the right kind of idea when you were sort of talking about what it would see, because that would involve sort of measuring things. And that's really what it's going to come down to, is nothing we can measure, none of the, not to do that, physical quantities can be referred to anything smaller than that region. So there's just nothing in the physics that is sort of sensitive. Maybe this is the way to put it, right? There's no physical quantities, no measurement, but just nothing else in the universe that it depends in any way, on what's happening inside that region, which is a way of saying there's, not only is there nothing in that region, there isn't even a region in that it is not even a region, anything smaller than that.
But when we conceive of motion in this picture, are we just imagining some object, call it P, and P is just sort of, if it's moving, let's say it is the size of the Planck area. Maybe that's a premise you won't want to agree with, but is it just sort of, it blinks out of existence?
Now, the object doesn't have to be small, right? We can just sort of say, where is its center of mass or something like that, right?
Sure, but is it sort of, well, I think that this picture, though, makes it a little easier to see why it seems...
So sort of talking crudely, and I'm not now pretending to kind of capture, in a completely faithful way what loop quantum gravity would say. But you can ask about this object, where is it?
Well, is it blinking out of existence?
Your answers, well, okay.
When it moves from one Planck area to the next.
So I'll answer it this way. You can ask where it is and sort of when it is. The only answers you're going to get are, with this level of granularity. So you're now kind of picturing space as a lattice. I mean, the whole thing's going to be quantum mechanical, so it's going to be more complicated than that. But if you were sort of trying to think about things in terms of a lattice, right? So like where the positions of the molecules in a crystal, something like the locations of the things. Then, yeah, if you ever wanted to know, wanted to measure or make sense of the question of where is the object, the only answers would be at one of those lattices.
Well, this is the interesting part, though, for me, because I think we're going to get right back to Zeno, which is, in this picture of motion, it's somewhat like watching a movie, in that there's the illusion of motion in that you see Brad Pitt walking across the screen, but what's actually happening is we're just seeing a quick succession of still images. So as our object is moving across this like quantum tiny space, it's just occupying these Planck squares in Planck areas in one instant, then another set of them in the next instant, and then another set in the next instant. But this brings us to Zeno's third paradox, which is, I think, called like the paradox of the arrow, where at every single instant, this arrow is just occupying its own space, and then in the next instant, it is somewhere else. So it's not really moving because it's at rest in every instant. And that, even though that was sort of my intuition for how the world, I guess, is not subject to the first paradox, even though this was how I thought the solution would look, it seems just as hard to imagine as the continuity version.
So right, awful lot to unpack there.
Yeah, awful lot.
First of all, I'm gonna sort of flag the use of the word illusion here.
Okay.
I mean, in the case of the movie, I mean, it really is sort of appropriate to talk about an illusion because we're talking about a psychological, event, out the way how we perceive how the thing is, how Brad Pitt is moving, right? Even though you're quite right, there's no kind of continuous series of impressions that we're getting. Incidentally, I think it's not clear that even when we're looking at things that are actually moving, that we're getting a continuous series of impressions.
You mean physiologically?
Yeah. Somehow at the neurological level, I mean, there's a continuous series of sort of images forming, on the back of the retina.
Yeah.
Well, they come in individual photons, so
right.
Not really continuous, but there's a fastest time we can actually process motion, and the illusions when if things are moving, if a spinning wheel is spinning at the right frequency, even just looked at, not just in the movie, it'll appear to actually rotate slowly, backwards. So, all right, but this is, sorry, I have kind of an interest in motion perception, but it's kind of a sidetrack, so I'll put that to one side and say illusion is that, it's like that. What I think you're getting at is not, I wouldn't sort of say an illusion, but would be, why is it actually that, even if something were moving discretely, sort of fundamentally, we can actually apply the calculus in which we treat it as moving continuously, and we won't go too wrong. The kind of answers that we'll get by treating the motion as continuous will be accurate enough, even though it's not really continuous. Okay, especially if we don't look closely enough. We don't have anything that can resolve the granularity of the motion. Why is it okay to use the calculus?
Are you asking me if that's what I'm asking?
I'm telling you that's what you mean by illusion there, I think.
Okay. Sure.
But so that you can have the opportunity to say that's not what you mean. But that's how I would take the question.
Okay.
So, but I think at the back of that also was, something you asked before, something about, is the thing blinking out of existence in between? But if this time is also, is also discrete, this is not a question that kind of makes any sense, because there is no, if there's, the object here at this time and here at this time and here at this time, and there's no there's no shorter distances, so that's the only places it can be. But if there's also no shorter times, it just doesn't make sense to ask where was it, at the time in between, because there is no time in between. Mm-hmm. And that's just the whole story. That's just going to be the whole story. If time is continuous but space is discrete, then it's sort of interesting. What's kind of happening? Does it sort of stay at that point and then instantaneously move to the next point? Or is it there for an instant and then it's nowhere for an instant? I don't know. Then it just depends on how the physics goes. Is that helpful? So there's ways of sort of thinking about it. But you've got to be kind of careful that you ask questions. We're setting up a system here, and then you have to be careful that you're asking questions that make sense within that system.
Yes.
So that would be kind of like that, how you would think about it. So, but it's not too hard. Okay, so to go back to, suppose space were discrete, things are really jumping around at the Planck scale. But suppose, as in fact is the case, when we look around, the smallest thing, I don't know, I'm not quite sure what the smallest thing a human can resolve is 10th, 100th of a millimeter or something like that. Much, bigger than the Planck scale. Microscope, you can see things much smaller. An optical microscope, electron microscope, you can see things down to the sort of atomic scale. effectively in the Large Hadron Collider in CERN, you can see things down to subatomic particle scale. But this is still far, far larger than our ability to sort of resolve any differences is far, far greater than the Planck scale. People do sort of back of the envelope calculations to figure out how big a linear accelerator you'd have to have, sort of using current sort of acceleration techniques to actually probe the Planck scale to actually see effects at this scale. And it's, I don't know, whatever it is, it's like the distance from the Earth to the Sun. It's an astronomical unit is how long this thing would have to be. All right, that's just one of those, how many football fields kind of things to sort of say how big things are. But okay, so nothing that we see is anywhere kind of close to being able to resolve anything at the Planck scale. So why not use the calculus? If I've got something that was somehow jumping along through my lattice, but I can just sort of pretend that there isn't, it's not a lattice, it's a continuum, and I've got something moving continuously. All I want is, at any of the times, if I want to know which lattice point it's at, I'm going to just use my continuous function, and it's going to be close enough to the lattice points. Indeed, if I use the calculus, it's going to say, oh yeah, the arrow is at sort of 10 meters now. But I can, if I can only measure that down to 1 millimeter, within that 1 millimeter, there are, an astronomical number of different points. My measurement accuracy, I can't resolve the Planck scale, so it doesn't really matter whether I'm not telling you exactly which lattice point it's at. So maybe that's a way of sort of saying yes to your question once I sort of interpret it that way, that there is a way of sort of, seeing how the calculus allows us to, is a sort of illusion, as it were, a stand-in for the reality of
so
Planck scale physics or something like that.
Quantum gravity and string theory are oppositional, right? They're two ways of trying to...
No, string theory is just a version of quantum gravity.
It is a version of quantum gravity?
So quantum gravity is the general idea of trying to combine gravity, so general relativity, the theory of space and time, with quantum mechanics.
And what do things look like at this very... I already asked you that question, so that's not what I meant to ask. What sort of things are near this scale? I mean, our protons are obviously far bigger than the Planck scale. So what do things break down to at that point? Is it tiny strings of some sort, or what is it?
So, yes, yeah. As the name suggests, yeah. So, I mean, at least people... This is a picture that was developed around in the 1990s. And people have kind of developed other ways of thinking about string theory since then. But in this sort of string theory picture, there's some of the fundamental objects are little one-dimensional strings, and because they're strings, I mean, they're like, I have a nice prop, which is a nice spring I can bring, and then I can wiggle it around, and you'll see that how it sort of vibrates. But just imagine a fairly stiff spring, sort of flying around in space, and if it gets bashed, it'll have vibrations on it. And the different vibrations correspond to the different properties of what we think of as elementary particles in high energy physics. So photons, gravitons that carry the force of gravity, and other sort of hypothetical elementary particles, and in more involved versions of the theory, sort of actual familiar elementary particles. But it turns out, so let me talk about the graviton, which is what carries the quantum force, and the photon, or if you think about gravitational waves. Right, so photons, are light particles, and so if you have enough of them, they build up into what we think of as a light wave. We know about gravitational waves, people know about that. So similarly, gravitons, a little quanta of gravity, and they add up to make gravitational waves. But it turns out they're not two different kinds of things. They're just different ways a string might be.
I see.
Okay, and so on for all the other particles. They're not all actually different kinds of things. They're just strings vibrating in different ways. And you might think, well, look, how can we tell that? Why don't we see that they're strings rather than particles? And the answer is the same. They're just way too small. So if you think about, you just imagine a very small kind of line. If you look far enough away, it's really hard to distinguish that from a point.
Mm-hmm.
Something like that. So that's the idea of string theory. And you can see why it's a theory of quantum gravity, because it naturally, that's one of the key features of string theory, is it naturally contains this particle, the graviton, which is exactly seems what you need for a quantum theory of gravity.
So everybody knows from chemistry that neutrons can be broken down into other subatomic particles. Are strings similarly decomposable, or are they, on this theory, the true atoms of the universe?
So, I guess neutrons can be broken down into quarks, right? So in that version of the theory, they really are. So in one sense, there isn't it isn't part of the theory that there's some different kind of constituent. On the other hand, they're dynamical things, and so one string can split into two strings, or two strings can join together to form a new string. So
if they're one-dimensional, if two strings join each other, do they just become twice as long in that one dimension?
Yeah, something like that. They are springs, so they have tension, so they're changing in length. It depends what's happening to them. But no, there'd be that. Yeah.
Huh. So are there? Do you have any interest in Zeno's other paradoxes beyond the ones that we've already spoken about? So there's this paradox of the moving rows, which
you mentioned the arrow. That's kind of a nice one as well.
Okay, sure.
The moving rows.
Yeah, there's moving rows. Then there's the millet seed, and then there's the paradox of place. But these seem to be much less.
What's the moving row? Did I write about that?
No, I don't think you wrote about that or the millet seed, or the paradox of place.
I think the millet seed's in there.
It is?
Isn't it in the article?
So the millet seed...
This has to do with sounds, right? Isn't it?
Yes, so it's like a heap of millet seeds. If you drop it, it makes a sound. Yeah. So...
Each one must make a sound.
Each one must make a sound, or each 100,000th of a millet seed must make a sound. But we know from experience, at least humoring Zeno, that if you drop a little seed, it's not going to make a sound.
Yeah.
But did you want to talk more about that one or the arrow?
No, it's not. Some of them really are sort of curiosities or something.
Yeah. Sure. So then the last question I guess I'll have for today is, I'm curious just about how philosophers work, because some seem to really spend a lot of time thinking, some just spend a lot of time writing. I'm curious what, in general, your work habits are like when you're philosophizing. Like, where do your sort of ideas come from, or what triggers your writing?
Right. I don't know where the ideas come from. Feels like it's inside my head, I guess, but I'm not sure. I think like a lot of people, it sort of goes through phases. Sometimes you have to be doing a lot of reading um, to familiarize yourself and to think about a subject, keep up on the literature. Other times I tend to go through periods sort of of intense writing, um, which sort of means writing 2 or 3 or 4 hours a day. I find I write best in the morning if I can sit down and then try to produce a lot then. I find for me, talking with people is really important. So talking to talking to people about what I'm thinking about, talking to them about what they're thinking about, getting their feedback, getting their ideas. I find that's very important. There's a lot of ideas, and that includes people working professionally. Teaching, I think, is another form of that. So, I mean, people say this a lot. I think a lot of people find this sort of figuring out how to explain or talk to it something, explain something to students can be very kind of clarifying. You really have to think in a very kind of clear way. You're really, once you're sitting there imagining a room full of 20-year-olds staring at you vacantly and pulling out their phones to check their social media, it's quite an incentive to be really clear and kind of interesting and gripping about what it is you're sort of saying. And that can be very kind of actually very useful, I think, for clarifying. But conversely as well, I mean, there's a lot of things I kind of, there's where I've explained something and students have just asked sort of questions or responded in ways I really didn't predict that really made me think differently about questions and learn something. So that's those kinds of interactions and similar interactions with sort of people. So I think, writing is good for really, I find that's really good for kind of clarifying what I'm thinking. And I try to imagine having sort of interlocutors who are listening to what I'm saying and how they'll respond. But then actually giving papers, talking to people, listening to other people's ideas, that's a really kind of crucial part of the picture as well.
You mentioned having, like, going through periods of lots of writing intensively or reading intensively. But what does an average sort of day look like for you, philosophically speaking? Like, how much time do you spend writing or read? Like, tomorrow, I mean, I guess tomorrow's a holiday, but and you're on sabbatical, so that probably changes things too. But how do you balance, like, the reading and the writing?
It really, it really kind of varies. It's really not balanced day to day.
And do you ever have dedicated time where you're just, like, staring and thinking? Or do your thoughts come out from, like, free writing?
So, I like to... there are definitely periods when I am thinking. So, but often that's when I will go for... you can't really do that, I find, sitting in front of a computer screen or something like that, something like that. I guess sometimes I'll sit there at a desk with my notebook if I'm really trying to think through some ideas and sort of try to sketch things out. I think a lot of the thinking happens, when I go for a walk, go to the park, go for a bike ride, sitting on the bus, when there's sort of not other distractions. Mm-hmm. I mean, I told you I'm on sabbatical, so maybe I'll have more of a routine of kind of work, but it partly it depends what needs to be done in terms of when I have to be reading to get up to date, or when I have time for writing. But working professionally, there's all kinds of teaching commitments and sort of service commitments, committees to sit on, papers to review, conferences to organize, reports to write, evaluations of colleagues to write. And so, that I find, and that's not continuous, so that also kind of causes disruptions to when you're working. I'm not really complaining about that.
Right.
That's part of the job, but that's just the sort of reality of it. But that's
Mm-hmm.
why something like a sabbatical is very nice, when you don't really have those distractions and you really can get into a routine of, of getting work done.
Okay, great. Well, thanks for giving me this insight into your work habits. That's nice too. I just like to see how other people work, see if I'm really doing everything all wrong. But this has been a really nice conversation. I learned a lot about Zeno. It's hard for me always to absorb the heavy science. In a conversation like this, I tend to be somebody that needs to read things over and over again, but I'm definitely going to listen to this again. So thank you so much, and I hope we can do a third one at some point.
Yeah, no, that would be great. And thanks for, the great and really well-informed questions. That was really good.
I have recorded this about 10 times because I'm just so bad at asking for help. But if you could like, subscribe, comment on whatever medium you're consuming this nascent fledgling podcast on, that would be so helpful, because the best thing for helping me grow this podcast at this point is making it at least appear that I have an audience. So thank you for listening, and thank you for supporting me.